So anybody would like to summarize, or maybe one by one, any major things that you have learnt new? Anybody?
Computing observation error covariances is new.
So I'm assuming that you guys already knew that the relative significance of observation error variances and the model error variances, right? So probably you guys already knew it, so it was just a refreshing thing. And the other thing that is that the model error covariance, the role of it, that it transmits informations of observation from one place to another, right? And it's also always not good to uniformly inflate artificially the covariances, this covariance inflation, because in regions of sparse observations, this can lead to a very increased model error covariance, and that will lead to, it will lead to what? Once and if an observation comes, it will lead to what? You guys remember? It will lead to too drastic a change in your analysis, right? And that drastic change will lead to spurious. Yes, so that drastic change will lead to something called assimilation shocks. And those shocks will propagate as spurious waves, right? And it can degrade your analysis. So the point here is that while doing data assimilation, we'll have to be mindful of multiple things, particularly when your system is complicated, like weather systems, like ocean systems. Okay? So these are the few things that probably we have learned. So now we have come up with another question. Is it always good to assimilate all the available observations? So did you give a thought in the last half an hour or so on this? Okay. So the point is, there are methodologies in which we can evaluate the impact of each observation on the assimilation, like whether it is having a positive impact or it is having a negative impact on the analysis. So by positive impact, I mean the analysis is getting improved. By negative, I say that the analysis is actually degrading. Okay? But how do we evaluate that? So there are essentially, to the best of my knowledge, there are about two such methodologies in use. One is called OSE, Observation System Experiment. Okay? And the other one is called EFSO, Observation Focus Sensitivity to Observation. It also has a non-ensemble counterpart, which is FSOI, Focus Sensitivity to Observation, FSO. Okay? Now, how can we do this? Like, what's the methodology? for OSE, observation system experiments, okay, what we do is, let's say I have different platforms of observations. For example, Argo, SST, then buoys, ship track, this kind of observations. So in OSE, what we do is we withhold some observations, okay, and do not feed it into the data assimilation system. Let's say we withhold all Argo observations, okay, or all buoy observations, and we do not feed it into the data assimilation system. The rest of the observations, we feed it, okay, and then we get an analysis, right? So this analysis we are getting from a limited number of available observations. Also, we can run another data assimilation experiment where we feed it with all available observations. So in one, all available observations are fed into the data assimilation system. In the other, we withhold some observations, and the rest of the available observations, we feed it into the data assimilation system. So we have two analyses now from these two experiments, okay? Just evaluating the performance of these two analyses will tell you whether the impact of all those withhold observations are positive or not. These kind of experiments are called data denial experiments, right? Because in one of the experiments you have denied the data assimilation system with some observations, right? So using this data denial experiments, you can evaluate the impact of observation systems on your analysis. If your analysis improves, you will say that it's better not to include these observations in the data assimilation system. And if your analysis degrades, then you will say that whatever observations I had withheld, they have a positive impact on my analysis. And it is better to include those observations into the system. This is called OSE, data denial experiments, observation system experiments, which is essentially a data denial experiment. The only problem with OSE is that it is very resource consuming, in the sense each time to evaluate the impact of each observation, you have to do multiple such experiments. Sometimes you have to deny this data, sometimes this data, sometimes this data. Only after doing multiple such experiments, you can come to a conclusion that XYZ is good and ABC is bad. So this is very resource consuming experiment. Okay? There is another methodology which is called EFSO or FSO. EFSO stands for Ensemble Forecast Sensitivity to Observation. Okay? In this experiment, you can measure the impact of each observation from one single experiment. Okay? That means that you are saving computational time and resources. But then, what are the drawbacks of this? The drawback of this is that you have to come up, or you have to design a weight matrix, something called a weight matrix, against which you will be evaluating the performance. So this was first done for atmospheric systems. So in atmospheric systems, what they did was that they chose the total energy, dry or moist, as the weight matrix against which this can be the impact of each observations were evaluated. The problem with ocean is that when you write the total energy of oceans for models like ROMS or MOM or similar, is that this total energy expression does not have an explicit salinity dependency. Okay, because of hydrostatic approximation. You guys are aware of hydrostatic approximation, right? So in all these hydrostatic models, when you try to write the total energy, the explicit dependency on salinity goes away. So that was the major reason why, as of now, or till recently, nobody has tried to do this kind of experiment on ocean systems. Okay? So we thought that we will give it a try. Okay? So even without a salinity dependency, we used the total energy, but then we saw that it did not work. We used kinetic energy, it did not work. We used potential vorticity. All of you are aware of potential vorticity? Okay. So that did not work. So eventually what we did is we came up with something called a baroclinicity vector. Are you guys aware of what is a baroclinicity vector? Okay. So this is what your baroclinicity vector is. Okay, a cross product of the gradient of pressure and the gradient of density. Okay, so this measures the degree of stratification that you have in your oceans or in your atmosphere, doesn't matter. How stratified your ocean is. So this will have a large value when you have a highly stratified ocean. Okay, for example, this value is large. So essentially, we have used a modulus of this. Okay, so this value is large in Bay of Bengal compared to that in Arabian Sea, because Bay of Bengal is more stratified compared to Arabian Sea. Why is Bay of Bengal more stratified compared to Arabian Sea? Why is it? Why is Bay of Bengal more stratified compared to Arabian Sea? Any insights? Yes, so there's a lot of freshwater flux that goes into Bay of Bengal compared to Arabian Sea. For example, rivers like Brahmaputra, Ganges. So all these rivers, they eventually go and meet the Bay of Bengal, and they deposit a large amount of fresh water into the Bay of Bengal. That makes the upper layers of Bay of Bengal quite fresh. The salinity is quite low in the upper layers of Bay of Bengal. In contrast, your Arabian Sea is less stratified because very few rivers go and meet Arabian Sea. The flux that is infused into the Arabian Sea is also small compared to Bay of Bengal. So the salinity on the top surface of Bay of Bengal is quite larger compared to that in Bay of Bengal. Okay, so the stratification in Bay of Bengal is much more pronounced than the stratification that we see in Arabian Sea. Okay, and we thought that why not make use of this. So we chose that vector, the modulus of that vector, to be our weight matrix. Okay, and we thought, let's see what it gives when we measure our analysis against this weight matrix. So the expression that you see for delta E, okay, has a very similar look like that of the cost function, except that there is a negative sign and all that. So your EA and EN are the errors in the forecast when an observation is assimilated and not assimilated. So EA is one when you assimilate that observation, and EN is when you do not assimilate that observation. So, okay, and when your delta E is negative, this signifies that your focus skill has improved. So you will get a delta E for each observation, okay, from one single experiment. You will do one single experiment, unlike your observation system experiment where you have to do multiple experiments. Okay, here you will do one single experiment. From that single experiment, for each observation, you will land up with a delta E. If that delta E is negative, then it signifies that it has improved your focus skill. If the delta E is positive, it will indicate that it's better not to include that observation. Okay? Oh, I can use this, right? So, in this plot, see, we have divided it into Arabian Sea and Bay of Bengal, just to look at the various impacts of it over these two regions. So this one is for Arabian Sea AS and this one is for Bay of Bengal. So this column is for SST, this one is for temperature, this one is for salinity. And what does it say? It says the red one is for all those, so this is over time, okay? The x-axis denotes time. So your red one says which the percentage of observations or the fraction of the number of observations which has a positive impact on your analysis, and the black says that which has a negative impact on your analysis. So from this plot what we see is that about 50% of the observations has a positive impact and about 50% has a negative impact. There are not, so yeah, okay. Now this plot is your delta E, what we had shown earlier, okay. So what we see is that first of all these temperature, salt and SST. So temperature salt is, we are getting it from the buoys and the Argos, okay, and SST is from the satellite data that we have. So what we see, and this blue color is for Arabian Sea and this orange is for Bay of Bengal. So what we see, the impact of SST, okay, on Arabian Sea is much more, has a much positive impact than the positive impact of SST over Bay of Bengal. Okay, so it makes more sense. See, first of all, both SST has a positive impact over both the regions, both Bay of Bengal and in Arabian Sea. So first of all, it's beneficial to include an SST assimilation over both Bay of Bengal and Arabian Sea. This is conclusion number one. Conclusion number two is SST over Arabian Sea has more pronounced positive impact compared to assimilating SST over Bay of Bengal, because this is more negative. Okay, the larger the negativity is, the more positive impact it has. In contrast, you see that it is more beneficial to assimilate your in situ temperature and salinity profiles in Bay of Bengal compared to that in Arabian Sea. Right? You get it? Okay. So what does this say? So this is your RMSC of temperature as you move along the latitude. The blue line is RMSC and the red line is correlation of temperature. So this is your Indian Ocean, and then we have three buoys. One is at, this is the equator, one is at equator, one is at around 4° north, the other one is at around 12° north. Okay? So there are three buoys. Correct? Understood? At the same longitude, which is 90 east. So here what we are seeing, okay, so the solid one is, okay, the star one is when you assimilate all the observations, okay. So once you assimilate all the observations, you do this EFSO experiment, okay. From there, you identify some beneficial observations, whatever beneficial observations you get, okay. In the next experiment, you assimilate only the beneficial observations. So you have now two experiments. One is where you are assimilating all observations. The other experiment is when you are assimilating only the beneficial observations, okay. So this star is when you are assimilating all the observations, and this solid dot is when you are assimilating only the beneficial observations, okay. Look at RMSC. So at 0° over here, over here at the equator, okay, there is not much of a difference in RMSC between this all experiment and this beneficial observation experiment, okay. But as you move northward, so this is at 4°. 4°, you see that your RMSC has decreased from the, using only the beneficial observation, your RMSC has decreased from what you had with assimilating all observations. As you move further northward, you see the RMSC has further improved. So if I assimilate only beneficial observations, I can improve substantially my RMSC the more I move northward. Okay? Same for correlation. Look at this correlation, which is at 12 north. Okay? And here. The correlation at 12 north for all observation is very close to 0. When I assimilate all the observation, the correlation is absolutely not good. But when I assimilate only the beneficial observation, the correlation turns out to be about 0.4. Okay? So this is RMSC and correlation of the thermocline. Yeah. Now,
Sir, why this changing is when the going from our side?
because of this we have chosen. We have chosen to evaluate it with respect to this weight matrix. So this weight, what does it signify? It signifies the stratification. Okay? The more north you go, the more stratified your ocean is, because most of the rivers dump it close to north. Okay? Okay. Another catch is here is, suppose I have a buoy observation. Okay? So let's say I have buoy temperature observation that observes in these locations. Okay. On day 1, it will give these locations. On day 2, again these locations, likewise and like forth. It will keep on giving observations each day. Okay. And each day I am performing this EFSO experiment. So each day, out of this, it might happen that these 3 are beneficial observations and these are non-beneficial observations. Okay? This can happen on day 1. On day 2, it is possible that these 2 are beneficial observations and all these 4 are non-beneficial observations. So this is going to evaluate it day by day. So one observation which has turned beneficial now does not necessarily have to be beneficial tomorrow or day after tomorrow or 10 days down the line. It can become detrimental, and then again over time it can turn out to be beneficial. So this plot tells you about, so for example, from one buoy, this is the plot. So the green one is your when that observation is beneficial, and red is when that observation is detrimental. So if you look at it at 65 degree, so this has been beneficial for 2 months almost. Then it turned at 65 meters. Then it turned detrimental briefly. Then it became again beneficial for a brief period of time. It again became detrimental, beneficial, detrimental, beneficial, and like that. Okay, what I was saying. So one observation which has turned out to be beneficial at some instant of time does not need to remain beneficial for your entire course of data assimilation that you are performing. So it can oscillate between beneficial and detrimental.
Sir, at what basis you are selecting this depth? You have some climatology, right?
No, I am not selecting this depth. These depths are buoys. So the buoy are giving you values at this depth, 5 meter, 15 meter, 25, 35. This is the depth of the buoy. This is giving me observations on each day from 2017 March onwards to 2018 May. Right? On each day I am evaluating whether this observation at 5 meter, whether it is beneficial or not. If it is green, it is beneficial. So what is it saying? From the initial, during March, it is beneficial. Then it turned red, which is detrimental. Then again it became beneficial, like that. Okay? Does not necessarily have to be. So what we are we have not yet implemented in our operational system while providing forecast. What has to be done is you have to run 2 parallel experiments. Okay? One experiment where you will evaluate that which observations are beneficial. Okay? And then once you have evaluated that these observations are beneficial, you will select only those beneficial observations, and then you will run a second experiment where you will feed the data assimilation system only with beneficial observations. Then you are going to get a much improved analysis, okay, from the second experiment, because you have only fed the beneficial observations. With this improved analysis as an initial condition, your forecast is supposed to be better. During forecast, you do not have observation, so you do not assimilate. Right? Forecast is ahead in time, in future. Is it clear? Okay. So how many of you know about OSSE? No? So OSSE is called Observation System Simulation Experiment. Okay, I'll just say briefly about this. I'll not get into this because we'll get into part B. So this is okay. So how do we use this experiment? Suppose, let's say I want to purchase 10 buoys. Okay, I have purchased 10 buoys. I need to install it. Okay, somewhere in the ocean. Where do I install it? To extract the maximum benefit from it. I can ask this question, right? I have an entire Indian Ocean. My institute has purchased 10 buoys. What is the best location to install these buoys so that I improve my forecast further? OSSE, Observation System Simulation Experiment, answers this kind of questions. Is this clear? Okay, so did you get any link? Everyone got, right? So now we will get into part B, but before I move on to part B, are there any questions? Because now we'll look at how to actually implement it. Are there any? Yeah, please. Which formula? That you have to try out. But for atmosphere, they already have one very well designated matrix, which is the total dry energy. So they have used it with total dry energy and total moist energy, both for atmosphere. So you can look it up. You can use it in your system also. It's well accepted.
Sir, how does we maintain its position at the time of extreme currents and representation?
How does it maintain its position?
Like you installed at proper latitude, longitude.
I will not be able to answer that question. This is ocean technology. I'm not sure how it maintains, but it does maintain. Yeah, what is the mechanism through which like it does not drift away? Is that what you are asking? Because of currents and all that? Most of the time it does not drift away, but sometimes it does drift away, and then there are retrieval teams that go and bring it back. So what exactly is the mechanism through which it remains in its place? I do not know. I will not be able to answer that.
The technical part is
Yeah, the technical part, how it is, I don't know. Yeah. So before we move on, any other questions? Okay. So how exactly do we implement LETKF, that ensemble system, in our place? So this is a pictorial representation of what is happening. Since this is an ensemble system, and we said that we work with 80 ensembles, okay? So each of these models, so there are 80 different models with 80 different initial conditions. So 80 ROMs, ROMs is the model that we use with 80 different initial conditions, 40 of which respond to one mixing scheme and the other 40 respond to the other mixing scheme. Okay? Each of these models are forced with different atmospheric fluxes, which are provided by NCMR WF. Okay? And the boundary conditions are provided by INCOIS CODAS. There is a global ocean model with assimilation as well. This provides the boundary condition to this regional model. We run this model for 5 days. On the 5th day, whatever observations we get from satellite, from Argo, buoy and ship, we assimilate all these observations using LTKF. Okay? Once we assimilate, there are two products from this. One is the analysis. The other one, using this analysis. Today I get an analysis. Using this analysis as the initial condition, I run my free model for another 4-5 days, which provides me the forecast. This is what is happening. Okay? Now, what is it within this LTKF that we will try to have a look at? Okay? Can you open your that folder that has been shared? Let me know once each of you have opened it. So you will find a tar GZ file. You have to extract it. Okay, tar minus ZXVF and then the tar GZ file name. This is how you will extract it. Did all of you manage to extract it? Huh? Getting downloaded. Okay. So for anybody it has downloaded completely? For some of you. So unfortunately you will not be able to run LTKF, but I am going to tell you how you can run LTKF once you go back. And I'm also going to tell you how you can kind of use it for your own models. I'm sure all of you do not run ROMs. So some of you might be running some atmospheric models, some of you might be running some other ocean models or some land surface models, I don't know. But after this, you will have some confidence of installing it in your own HPCs, and you will probably be able to modify this according to the models that you run. All of you are fluent in Fortran? No? So this code is entirely written in Fortran. Fortran 90 with, and then there are parallel computings also involved. MPI. So you guys are aware of parallel computing? Great, at least some of you are nodding heads. So anybody who knows both Fortran and parallel computing are at an advantage here. So download is complete for all of you? Anybody still downloading? Yours, how far? 2% remaining? 2 minutes. His is complete? Huh? You can share na that system.
I am uploading
You are?
my HPC.
You're uploading it to your HPC?
Yes.
That you can do later on. Now you share.
It is uploaded. 65% uploaded.
That's fine, but you will not be able to run it now. So keep it in your local system. All these exercise you can do once you go back. So, okay, you will see that there is one doc file LTKF doc, right? It explains the entire architecture of the code, what each module does, what is the purpose, and kind of in brief how it does it. Okay, all the important modules that are there. It is written for some other ocean model called MOM, but then the philosophy is same for ROMs also. So anyway, you will not be using it for ROMs, you will be using it for your own model. What you need to understand is what each of these module does. That you will find in that doc file. There is a PDF file. So you can open the PDF file, you can browse through it, you will understand what each of the subroutines or what each of the module does. Okay? Now we will open this Ocean LTKF ROMs folder. Okay? Can all of you please open this folder? Within this folder, you will see that there are 3 directories. One is config, the other one is common, and the other one is ROMs. Okay? Please go ahead and open the config folder. In that config folder, you will find 3 shell scripts. One is machine.sh, one is machine_fortran.sh, and the other one is machine_netcdf.sh. Okay? So in the HPC that you will be working on, that HPC I am hoping has a name. For example, the HPC that I work on has a name called Mihir. Some other HPC name that IITM works on has a name called Aditya. So I'm hoping that the HPC name that you will be working on will have a name. Okay? So in that machine.sh, all you have to do is provide that name of that HPC. Okay? In machine_fortran.sh, since each of these HPCs has different architectures, some has compilers like FTN, some has compilers like MPI ifort. So these compilers can also vary from one architecture to another. So the Fortran compiler that is compatible with your HPC architecture, you will mention that in machine_fortran.sh. Okay? Right now, if you open this machine_fortran.sh, what do you see? FTN. Can you open machine_fortran.sh? What is it written? The compiler? MPI ifort. Okay, so it's MPI ifort. Okay? Next, so these two are clear to you all? Okay? So in machine.sh, you will write the name of the machine. In machine_fortran.sh, you will mention the compiler. Which compiler you are using, whether it is FTN or MPI ifort or whatever it is. It has to be a Fortran compiler. Remember that. In machine_netcdf.sh, if you open that, you will have to provide the path to your netcdf libraries in your HPC, okay, where it is stored. So different HPC, the path will vary from one HPC to another HPC. Clear? Okay? Okay. Now we'll move on to this ROMs folder. Come out of this config folder and go to the ROMs folder. So within ROMs folder, there are, again you will find 3 folders. Sorry, 2 folders. ROMs will have 2 folders, LTKF and OBS. Okay? Within LETKF and within OBS, you will find two shell scripts. One is make letkf.sh and the other one is make observeall.sh. Okay? One shell script you will find within LTKF folder, the other shell script we will find within the OBS folder. So these are actually, both these shell scripts are actually compilation scripts. If you provide correctly your machine name, your Fortran compiler and your netcdf libraries, okay, then you should be able to compile both LTKF and this make letkf.sh and make observe all sh. Both shall run successfully. This will help you to compile the codes. Okay? Great. Now what are the important programs that you will need to suit this LTKF for your model? Okay? So can you go to this LTKF folder? There you will find one program called params letkf.f90. Everyone please open that program, params letkf.f90. Okay? So here you will have to specify, you will find one variable called NBV here as a parameter. Can all of you see it? NBV. That is actually you are mentioning how many ensembles you are working with. If it is 20, you will mention it as 20. If it is 80, you will mention it as 80. Okay? There is also another variable which mentions the covariance inflation. It's written, there must be a comment on it. Yes. So this COV_INFL_MUL. So that is your covariance inflation multiplicative factor. Okay. So if you put it as 1.1, this means that you are asking it to have a 10% inflation. 1.05 is 5% inflation. Okay. You can keep it at 1 also. 1 means there will not be any inflation. ठीक है?
No inflation. One means?
No inflation. There won't be any inflation. Okay, essentially it's a multiplicative factor. So you have your analysis you are multiplicating with this factor. So you are multiplicating with 1 means you are doing nothing, keeping it same as it is. Okay. Next, can you open params model.f90? Did you open, everybody? So this is where you have to specify your model grid and all that. The number of longitudes that are there in the model, the number of latitudes, the number of levels, all this you have to mention in params model.f90. All the model specifications.
What is end? And team.
See, this is you don't.
This is the level
This
long.
you don't need it. It's only for relaxation files. You won't need L-time, N-time. Okay. Okay. There are here. If you scroll down, you will see another 2 parameters, which is NV3D and NV2D. Okay. Can you see it? NV3D and NV2D. This tells you the number of NV3D means the number of 3-dimensional variables that you have in your model. For example, in ocean, the number of three-dimensional variables that we deal with are U, V, temperature, salinity. 4. Okay? For atmosphere, you have to modify it accordingly. Okay? NV2D is the number of two-dimensional variables that we are dealing with here. Here, in this case, you will find NV2D to be 3 because we are dealing with SST, sea surface salinity and sea surface height. Okay? This is how you have to modify this, your model param. Okay?
And where NV surface you have put in,
Not needed for you guys.
but sea surface temperature.
That is in NV2D.
Okay.
So if you move down, you will see there are things like IV3D underscore U, IV3D underscore V, all those, right? So each one of these mentions it's a tag for each of these variables. So for U, it is 1, for V, it is 2, for T, it is 3, for S, it is 4. Okay? Similarly, for SSH, SST and SSS, there are numbers. So it is just tagging this. Okay. So now we will move on to this LTKF.F90. Okay. So this is the main program that is being run here. So what does this program do? So we'll just briefly look at what this program does. Okay. So these are all the subroutines that this program calls. You will see if you open, there is something called call initialize MPI. Okay. So this what it does is it breaks your entire domain into small tiles. Okay. And then each of these tiles it sends to each processors. Okay. Then call set common ROMs. This is a very important program. Okay. So call set common ROMs is in common ROMs. It is just. Is it Linux?
Yes.
Can we just open the terminal? Okay. So in Ocean LTKF ROMs, within ROMs, you will find there is another folder called common. Okay. Within common, you will find a program called common underscore ROMs.F90. Just open that.
Which one?
Within ROMs, you have a folder called common. Within common folder, you will have a program called common underscore ROMs.F90. Open it. Okay. So within that, there is a subroutine called set common ROMs. Can all of you see it? Set common ROMs. Okay. So this is the subroutine where your model is read by the program. Okay. All your model variables. For example, here, this is the subroutine that reads the temperature, salinity, velocity, this, that, everything. So for when you will try to modify this program for your model, you have to work extensively on this program because you might have a different variable, you might have a different different model, even how that model, so here each of this is written keeping in mind that the model output that we get are in netcdf file. Okay, so do all of you get your model outputs in netcdf files? So I'm hoping for atmosphere and ocean science, all of you will be getting it in netcdf files. If you do not get it in netcdf files, then you have to modify it accordingly. So here it is written in such a way that netcdf libraries are used. If you have some other HDF format or some other format, then you have to start with that make netcdf.sh, machine_netcdf.sh. There you have to mention. Anyway, so here you will be reading all your model variables. Basically, this is where you are reading your background state, XB. Okay, good. So, this is what is done in here. Now, once you read your background state, you read the background state for the entire domain, right? But then in initialize MPI, we have divided the entire domain into tiles. Okay. Next, you will see that letkf.f90 calls upon a program called set letkf obs. Okay. This is where the observations are read. So here you read your model, here you read your observations. Remember in LETKF, in this routine, all the observations that goes in are already quality controlled. Okay, there are some very basic quality control within it, but when you send observations, when you feed your data assimilation system with observations, please do a quality control and then send it. One. Next is you will have to send it in a binary format. The program is written to read your observation files from a binary file. You know the binary format, right? Do not feed it with an ASCII format. Remember this, feed it in a binary format. Okay? So this is where it reads all the observations. Okay. Then it reads all the ensembles. Okay? From those ensembles, still we have not done any assimilation. What this does is it calculates the ensemble spread and mean of the background state. This call write ensemble this calculates the ensemble mean and the ensemble spread of your background state and then writes it out. Okay? And then stores it in some file. My background ensemble and background mean. This thus LETKF is where the assimilation happens within this module. Thus LETKF. Okay? Once that assimilation happens, then you get an analysis ensemble. Okay? From that analysis ensemble, again, a similar write ensemble MPI. So this is where it writes out each of these ensembles into a netcdf file. Okay? And then last, again, from all these analysis ensemble, it finds out the mean and then also the spread and stores it again in a netcdf file. This is what it happens in entirety. So I'm pretty confident that if you go through the doc file and you go through that code, you can actually do it for your own system. You cannot do it overnight, let me tell you. It will take you 2 to 3 weeks, 2 months, if you work diligently, depending on how much time you are giving it. So the first hurdle that you are going to face will be to compile it. So just try whatever I have said. Just go through that make script, and then from the errors you will understand where you are going wrong, if there are errors, and then you can modify it. And then just read that paper by Bryan and Hunt, that one on that original paper on LETKF. Within that paper, they have mentioned the flowchart of how to do this data assimilation. The code follows exactly that same procedure. Okay, this is all fine. Now, how do we exactly implement it in your system? See, you will have to do it in a cycle. It's not that you are doing data assimilation for one time step. You will have to continue it. So how do you maintain that continuity? Are you getting what I'm trying to say? So today I have my background ensemble. Today I have all this observation, right? Using all this, I get an analysis. And I get 80 analysis, 80 analysis and one analysis mean. So using this 80 analysis, I'll be running my data assimilation system again. I'll be moving forward, correct? So how do I kind of automate this? There is something called Rokoto. If you have not heard of it, Rokoto is a workflow management system. So these are all the practicalities now I am talking of. Okay. So Rokoto is a very efficient workflow management system. To know more about Rokoto, you can always visit this page. This guy, Christopher, developed it. Okay. So the first thing that you have to do is you have to ask your system admin to install Rokoto in your HPC. Okay, if you want to run ensemble systems. For ensemble system, this is a huge help. Okay. And this is how you run a Rokoto. Rokoto run is a command -w. So you will be writing an XML file, and then -d, and then Rokoto will give you back a log file. Okay. So I'll come to it. So what Rokoto does, think of it, is that you have given a run. You forget assimilation or anything. Let's say you have written a script, a shell script, to run 80 versions of the model in parallel. So some processors are running model 1, some other processors are running model 2. Like this, 80 models are running in parallel. Okay? For some reason, one model does not finish its run. It comes out, it blows up or something. Okay? The kind of script that we are accustomed to is we will again have to run the entire script. We will fix whatever has happened with that particular model, we'll fix it, and then again we will run all the 80 models. Using Rokoto, that is not needed. Whatever run, let's say 79 models have completed. That is completed, whatever model it did not run, you can again run it without repeating that 79 runs. Okay? So, So how is that Rocoto workflow that we have used? So we start with, there is something called, over there you will find a script folder. Can you just show me? Go. You go to Ocean LTKF ROMs, then there is a folder called Retro Run. Within Retro Run, you have a folder called 1x12. There are so many. So the entire path of where I am is Ocean LTKF ROMs, then Retro Run, then 1x12, then No Relax 5 days. Okay? Within this folder, you will find that there are various scripts, KSH scripts. Okay? So these are the scripts that I am talking of here. So you have a template of these scripts also with you now, how to write these scripts. And the Rocoto script is run XML. You open this, run xml.rocoto.ltkf. Okay? So here, if you open it, you will see that there are certain definitions. We have defined some root, something called a root. Okay? Entity means that is an entity called root, which has a value /home/this/this. Okay? So root is, the entity root is assigned this value. Right? Then the entity storage, scripts. So these are all, if you look at it closely, you will see that these are all paths that has been assigned. Okay?
Root means where model with the which folder?
It all depends on how you want to write it. Then there is, you will find another called input init. So this input init is where you keep all your inputs. Okay? So this you modify it according to your own requirement. Then you will see something called a start date entity. So the start date is the date from which the model is going to, or your data assimilation system is going to start to run. Okay. I can't hear you. Okay. So this AND symbol, for example, you go to this exp_data. Okay. So in exp_data, you will see it is assigned the value AND storage. So this essentially means that exp data, the value of exp data and the value of storage data is same. You will find an entity called storage, the second entity, right? So your exp data and storage, they have the same value. And storage means take the same value of the storage. Okay? And but in the next line itself, see log. Log is and storage /log. So when you use, so this is, you are augmenting it. So storage, and then you are adding that /log to it. Okay? Fine. So here also you need to define how many ensembles you are working with. If you scroll down, you will see there is something like members underscore 04, members underscore 10, like this. So here you have to say, you have to assign numbers for each ensemble. Like here for 04 we have assigned 01, 02, 03, 04. Okay? So if you are working with I-80 ensembles, you have to mention all this for once. Then you will see max tries. There is something called max tries. Here I am saying that there is a value 14. So like I mentioned before, if one of your model out of 80 models does not work, then Rokoto will try again. So this is the number of tries that the Rokoto will perform before actually giving up. So it will try 14 times to run it. Okay, here, if you write it 2, it will try 2 times. Okay. So you will have to mention where your all the, so how, okay. So how do you use these entities? Okay, in your script. So if you open any script, you open, let's say you open model.ksh. Just open that script. .ksh. Yeah. Did you open model.ksh? See here, using dollar, we have used one of the entity called exp underscore data. So once you have defined it in the XML file, you do not need to define exp data here. It will take it from that XML file. Is it clear? So all this, so what it does, the Rokoto workflow is, it starts with start.ksh, where there is a trigger. We have just used the trigger to start it. Okay? Then it goes to model prep. So you have 80 ensembles, or I have 80 ensembles to work with. So it prepares those 80 such model configurations. Okay? Then there is model.ksh. In model.ksh, it runs all these 80 models in parallel. Okay? So sometimes what happens is not all processors are available. So 20 will run and then the rest of the 60 will stand in queue and like this. So your model.ksh will be triggered only when your entire model prep.ksh is over. So model.prep will wait for model.ksh to get over. Okay? And how you can ensure that? That also you can ensure in your Rokoto script, that XML script. In that XML script, if you go, you will see that there are certain called task name. In the task name, that search by model prep or model.ksh. In that model.ksh, if you search, you will see that there are dependencies. Only when those dependencies are met, that your model.ksh will be triggered, will be fired. Let's say, just giving you an example, I write this model prep.ksh in such a way, this model prep.ksh in such a way that once this entire model prep gets over, one file will be generated. That file will not be generated unless the entire model prep gets over. So I can mention the name of that file as a dependency for model.ksh. Only when the model.ksh will start running, only when it will see that file has been generated. Before that, it will not start running. Clear? So, model.ksh, what it does, it runs all these models. It will try to run it all in parallel if there are processors available. If not, in staggered way it will run. Sometimes 10, and then as and when it will get processors, it will fire the jobs. Okay? Once model prep and model.ksh is over, then comes LETKF prep.ksh. Here there are certain folder structures that it maintains for easy evaluation. So in LETKF prep, you will bring all those, you will actually arrange your background model state and your observations in a very disciplined way. That's what LETKF prep.ksh does. And then next, again, it's LETKF.ksh. That is where your assimilation is done. Once it is done, it will again go back to your start.ksh. And then this cycle will keep on repeating. And how do you end this? So you end this there in your Rokoto script. You have this is the Rokoto script? No. Open the XML script again. So go to line number 193. Can you see there is something called a cycle def? Line number 193 in the XML script. Everybody? In the XML script. Run Rokoto was the name. Did everyone open that XML script? In that XML script, line number 193, there is something called a cycle def. In that cycle def, there are two numbers. One is 2016-0815-0000, and next to it is 2018-04-30-0000. The first number is from when it is going to start, okay? And the next number is when it is going to end. So in this case, the first number signifies that it is starting from 15th of August 2016 at 0 hour 0 minute. Okay, the last four zeros stand for HHMM, 0 hour 0 minute. And it is going to end at year 2018, 30th April. So it's in YYYYMMDDHHMM. This is the format. Okay? Write it. So, this is the format. Year, month, day, hour, minute. Okay? And days is for how long it is going to run. For example, I'll start with 15th of August 2016. I want my model to run for, it's actually the cycle frequency. Days is actually the cycle frequency. Here, how much it is? Days we have defined above as an entity. So days is here defined as 5. So it will run for 5 days, and then again it will go to start.ksh, like that. It will happen. Okay? And you always put your this Rokoto script. So this script, so in this particular case, you Rokoto run minus W, this XML script that you have written, here you will mention that, minus D, and you mention a log file name of your choice. Okay? And how do you run it? You write this entire in cron tab minus E. So have you guys used cron tab? So in your, see, do you have a cron tab? No cron tab for Nishu, okay. So install cron tab in your HPC, it will be there. So just write cron tab minus E, then like you do VI, page opens. Similarly, cron tab minus E, it will open a page. In that page, you write Rokoto run minus this, and then you exit, save it and exit. That will keep on running in the background. How do you check? For checking, you have similar, same command, except that your Rokoto run will be replaced by Rokoto stat. Okay, so Rokoto stat will tell you what is the present status of the run. Then there is something called Rokoto rewind. If you want to run again some previously completed cycle, that also you can do using Rokoto rewind. Maybe let's say you want to run a cycle of, so at present you are on 15th May 2024. Let's say you want to run the cycle of 15th May 2023. Then using Rokoto rewind, you can run that cycle. Okay? So Rokoto has a lot of advantages that you can make use of. So I'll highly recommend you guys to, if you want to continue working on data assimilation and ensemble systems, even if not ensemble systems, on numerical weather or ocean systems, just as a modeler, giving jobs to high performance computers and all that through Rokoto has its own advantages. Just try to give it's easy, not very difficult. Just give yourself some time, you'll be able to run jobs through Rokoto. Only that you have to ask your system admin to install Rokoto. Okay? So, oh, excellent timing. Yeah. So any questions that you have? In case you face any problem, you can always drop me an email. Okay, I'll try to help you out. Any questions? I don't. I don't think I'm that good a speaker that you guys have understood everything. That's not possible. I do hope that you guys are taking back something with you from this lecture. I don't have questions.
So let us all thank Dr. Arya for this hands-on with
Not
the
exactly a
CELITY.
hands-on. Not exactly a hands-on.
Okay, so you have at least given them the sort of framework and the codes and shared everything so that they can go back to their respective institutes and run it. Yeah. So let's give a good standing ovation to Dr. Paul.